Hello everybody. In this video we want to continue the discussion of countability by presenting a theorem that basically lists a whole bunch of nice properties of how to take countable sets and combine them and make sure you still are getting countable sets. In order to prove the countability Omnibus Theorem, we're going to start with a countability lemma, right? And this is essentially going to be inspired by our proof of the countability of the rational numbers. So let's start here with this lemma that we'll call the countability lemma. So what the countability lemma says is, well, let's see. Let's start with a set A. And let's say we have found some function, call it f, from A to the positive integers. Okay, so let f be a function. All right, so here's the statement where our goal is to show that A is countable, and a sufficient condition is that if the f preimage of every positive integer, okay, so remember what this means, I take a positive integer and I ask what are all of the elements of A that map to it, all right? So if I had my picture here, positive integers, I had my A, I have this function f, I choose some positive integer and I ask what are all of the different points which map to it. Okay, and I don't know anything about A, so maybe there's no points that map to my given point, or maybe there's 3 of them, like in this picture, or maybe there's an infinite number, right? So we don't know, but if we somehow do know that the preimage of every point is finite, okay, so that this, remember the f preimage kind of had 2 different meanings, and one of them it's the set, right, of all elements of A which map to this given positive integer. If the f preimage is finite for every positive integer, then A is countable. Okay, and we're going to be able to use that to great effect. All right, so let's give a proof of this. And if you go back and watch how we proved that the rational numbers were countable, you're going to see some overlap here. All right, there's going to be some similarity. Okay, so first, let me start with some positive integer. And I want to set, I don't know, give a name to it like P sub n. So P sub n is going to be a list, all right? So it's actually like a set, but there's an ordering. So I use this parenthesis notation in that case. And I'm going to look at all the elements in A, okay, call them little a, such that when I apply this function f to little a, I get the number n. Okay, now that's not an inherently ordered list, okay, because like I take this collection of a's which map to n, okay, but what we could do is just assign them some order. It's some finite list, okay, because we're assuming the f preimage of every positive integer, like n, okay, and that's all Pn by the way is, right? This is the f preimage, but given some sort of ordering. So I could even write it down with symbols. I could say like, okay, since I'm in the nth position, I'll use an n superscript, and then there's the first one after I order it. Okay, and again, there's no rhyme or reason to the ordering. You just pick an order and stick to it. Okay, and then I could maybe have a second one, and a third one, and so forth, and it's going to stop at some point, right? I don't know what that is, but it's some number that depends on n, right? So I could write like k sub n. Okay, so that's what p sub n has to look like. Okay, and again, I know it stops because of the assumption that the f preimage is always finite. Okay, now it also could be that there are no preimages, right? I might have some point, some positive integer, and nothing maps to that positive integer, in which case I'll just define it to be this empty list, right? So if n has no preimages, right, or f preimages. Okay, now in order to show that A is countable, I need to define a bijection from the positive integers to A. All right, so we need to define a bijection, call it G, from the positive integers to A. Okay, and so here's how I'm going to do it. Okay, I'm going to work through these P sub n's in order. And within each P sub n, I will work through them in order. Okay, and that's basically it. So as an example, let's say that I know that my P1 has 5 elements in it. Okay, so let's just put this on the side. So let's assume this is an example here, that P1 has 5 elements. Okay, that's the first of my P's, right? I start with n equals 1. And what I'm going to do is just define G of 1 to equal A11. And then G of 2 will be A12. And G of 3 will be A13. And G of 4 will be A14. And G of 5 will be A15. Okay, so I've made my way through P1. Now I go to P2. And let's assume that P2 has no elements in it. Right? There are no preimages of the number 2 with this function f. Okay, I just move on. Now I check P3 and I say, oh, that has 2 elements, say. So now G of 6, whoops, I wrote G5 here, but G of 5. So G of 6 is going to be, well, I'm in the third P, and I look at the first one, and then G of 7 is going to be in the third P, and I look at the second element in there. Okay, and there's only 2, because I said P3 has 2 elements. And I just continue in this way, all right? And in this way, I've defined G for every positive integer. Okay, so that's how we're going to do this, right? So it's in the same way when we did this for the rational numbers, it's kind of a descriptive statement here of how we're actually going to do it. So we'll just say we define G by working through the Pn's in increasing order of n. And within the Pn's, by working through the list in increasing order. Okay, so that's what's going on, and we see the example. Okay, so see example. Okay, so that's the idea. So there you go. And, oh, by the way, why is it a bijection? Right. Well, first, does every element in A get hit? Well, sure. Every element in A gets mapped to some integer, so it's in some P sub n. Okay, so definitely it's going to show up at some point. So we have surjectivity. How about injectivity? Well, if I had 2 different G's going to the same number, well, how would that even happen, right? Because I'm going through each of these P's one time, and I go through each of the elements in the list one time. So I get injectivity, right? I can't go back and hit this exact same element of A twice, because it only shows up, right, in one of these P sub n's, because f is a function. It only sends an element to one specific positive integer. Okay, so that's why we get that it's a bijection. Cool. So now let's get to the Countability Omnibus Theorem. So the Countability Omnibus Theorem. This is just a bunch of stuff we're throwing together into one theorem. So I just need a whole bunch of sets here at the beginning. So I'm not even going to, it's so long I don't even write it out here in full sentences. So A and B are going to be sets with B countable. And then I'm also going to have an infinite collection of sets. In fact, I would say countable sets. A1, A2, A3, etc. Okay. And actually, let's make an even bigger assumption. Let's say that A is a subset of B. Okay. So our first statement is that, well, we know B is countable and A is a subset. And so the claim is that A is finite or A is countable. Okay, so in particular, you cannot have an uncountable subset of a countable set. Okay, which, I mean, in the sense of sizing, right, that should make some sense. You say, oh yeah, well, I can't get bigger by going smaller, right? Now, there are some times in math where that doesn't work out anymore, but in this case, it works the way you expect. Second, let's say I take the union over all of these A sub n's, right? So I take the union over all A sub n. So that's a union of countable sets. And the claim is that this is also countable. Okay, third, what if I take a Cartesian product of these A's? Well, it turns out that if I take a Cartesian product of all of the A's, so that would be a countable Cartesian product of countable sets, that actually may not be countable. That actually should be uncountable. But if I stop at some point, okay, any point, right? I just stop somewhere. So I take a finite Cartesian product of countable sets. This will be countable. So this is countable for all positive integers. Okay. And then finally, one more. If I take the set of all finite subsets of B. So B is some huge countable set, right? It's an infinite set. But I can look at subsets, which only have a finite number of elements. And I take the collection of all of those subsets. That will be a set. And it turns out that this is also a countable set. Now, this word finite is actually really important. If I just take the set of all subsets of B, don't restrict myself to finite subsets, I will get an uncountable set. All right, well, we're going to prove some of these. So I'll probably prove the first three, and I'm going to leave the fourth one as an exercise. But what you'll see is using this countability lemma, all of these proofs end up kind of looking the same. It's just a matter of how, when we go back to this countability lemma, how do we define a function from the set we're trying to prove is countable to the positive integers such that each positive integer has a finite f preimage. Okay, so we'll see some examples here, and you just see how the game is played. Okay, so first, we have a countable set B, and we have a subset A, and we want to prove that A is either finite or countable. Well, A could be finite, right? So if it is finite, we're done. So we might as well just assume A is not finite. So if A is not finite, then, of course, we need to show it's countable. Then, okay, we need to show A is countable. Okay, well, what do we know? Well, we know B is countable. So since B is countable, then we know there's some bijection from the positive integers to B. Okay, so there is a bijection, and I don't care about the name of it, but there's some bijection from the positive integers to B, which means I can assign to each positive integer some element of b. So 1 goes to some b1, and 2 goes to some b2, and 3 goes to some b3. So in fact, I can write down all of the elements in b. So we can write all of the elements in b as b1, b2, b3, etc. And how do I know everything in B gets hit? Well, because this was a bijection, so it's surjective. So everything in B is the image of some positive integer. Okay, so I'm going to write everything in B in this way. Now I want to use this to define my function from A to the positive integers. So we're going to define some function f from A to the positive integers in the following way. Okay, what do I have to do? Well, if I'm given some A in A, I need to send it to some positive integer. How do I do that? Well, if A is in A, well, we know A, big A, is a subset of big B. And everything in big B looks like B1, B2, B3, etc. So then we know there exists some positive integer n such that A is equal to B sub n, right? If A is in A, then it's in B. And if A is in B, then it's one of the items in this list. Okay, so it looks like B sub something. Okay, so maybe B sub n. Okay, so in that case, we define A to map, well, of course it's f of A, but what are we going to map it to? We're going to map it to, not B sub n, but just the n. We just take the index. All right. So the way you might think about this is if I write down all the B's, every once in a while, I'm going to get an element of A, right? Not all of them are in A probably, but some of them are. So I start writing this down, B, 10, etc. It goes on and on and on. And let's say there's something in A, and 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 so forth. So everything in A shows up on this list, and where do I map this? I map that to 2, and I map that to 4, and I map that to 5, and I map that to 7, 8, 9, etc. Okay, so I now have a function that sends elements of A to the positive integers. And note, I can only send at most one element to a positive integer, right? So if I take 9 as my positive integer, B9 got sent to it. And that's the only element of A that could get sent to it. So in fact, the preimage of a positive integer is either, well, nothing, like 1, right? Nothing gets mapped to 1. Or the preimage has one element in it. Namely, something, okay, if I take 2, well, B2 got mapped to it. Okay, so we've just proved that f is a function that for every element in the positive integers, there is at most one preimage. Okay, so the preimage, right, or the f preimage of every n has at most one element. Well, 1 is finite. So by the countability lemma, A is countable. That's it. That's the whole thing. Once you know that you have a function such that every positive integer has a finite number of preimages, then you know your set is countable. Okay, beautiful. All right, let's go to the second problem. Okay, second one, we're trying to show that if I take a union of countable sets, right, and this is an infinite union, right? This is all n at least 1. So this is a countable union of countable sets. We want to show that that is still countable. Okay, so I want to play the same game. And so what I'm going to do is the following. All right, I need to define some function from the union to the positive integers. So if I take some element in the union, I need to map it somewhere, right? That'll be our g of a. And the question is, where do I map it to? Well, here's what I can do. By the well-ordering axiom, remember we abbreviate that WOA. By the well-ordering axiom, and we can use the greater than or equal to 1 version here, every one of these sets, right, is indexed by something at least 1. If I take this little a, it's in the union, which means it needs to appear in at least one of the a sub n's, but it might be in many of them. But by the well-ordering axiom, there is a first a sub n that it appears in. So by the well-ordering axiom, there exists a minimal, let's call it I, greater than or equal to 1, right? Or if you like, it's a positive integer, such that A is an element of big A sub I. Okay, so that's the first of these countable sets where this element little a appears. But now we know that A sub I is countable, which means there's a bijection from the integers to A sub I, which means I can write down the elements in A sub I in a list. So it looks like maybe A sub I1, A upper I2, AI3, AI4, etc. Which tells me that there is some item in this list equal to A. Okay, so let's see. Oh, I guess I should just use curly braces there, although I could write them as an ordered list. Okay, so A is in there, so there exists some positive integer j, such that A is equal to AI sub j. Okay, so first, by the well ordering, I know there's a minimal I, such that A is in big A sub I. And then once I'm in that countable set, I can just figure out, okay, where is it, right? I've ordered these things in some way. Which of these is my little a? Okay, and that's A upper I lower j. Okay, so now that I have this description of my little a, I know it shows up in the ith set in the jth position, I can define my g of a. I'm just going to take I and j and add them together. Okay, and that gives me some positive integer. Right? Okay, but for the countability lemma, we need to make sure that every positive integer has only a finite preimage. Well, how do we know that? Well, what I claim is that every positive integer n has at most n minus 1 g preimages. Okay, and n minus 1 is definitely finite. Okay, now why is that true? Well, what are they? I mean, I can write down what they could be, right? Now, it turns out like not all of these necessarily will be preimages, but this is the best we can do. I need to choose elements, they look like A, I, j, such that I plus j is equal to n. Well, how can I do that? I could do, well, for starters, how about A1, n minus 1? These add up to n. Okay, or I could do A2, n minus 2, or A3, n minus 3. And I could keep going, and eventually I'll get to A, n minus 3, 3, and A, n minus 2, 2, and A, n minus 1, 1. And that's it, right? That's the only way I can take positive integers and add them up to n, right? If I take two positive integers, add them up to n, I'm just partitioning up into two pieces, and these are all the possible ways I can do it. And you count along the top, and you see 1, 2, 3, n minus 1. There's n minus 1 ways to do it. Okay. Now again, it may not be that all of these are preimages, because it could be, for example, you're looking at A5, 8, and that would only be a preimage if this element A you chose, it showed up for the first time, right, in the eighth countable set, and maybe it didn't. Maybe it showed up in the 6th already. All right. So okay, so that could be, but it doesn't matter, right? If it's smaller than n minus 1, we don't care. So the point is, all right, this is a finite set of preimages, and therefore, by the countability lemma, by the countability lemma, the union is countable. Isn't that nice? So all we have to do is come up with this clever way of assigning integers, positive integers, to the elements of our set, but we have to do it in such a way that we don't get more, an infinite number of elements going to the same positive integer. Okay, we're going to do the third one, and again, I said I'm going to leave the fourth one to you, but let's look at the third one now. So the third one, remember, we're looking at a Cartesian product. Okay, so remember Cartesian products, this is going to look like some, A, what do elements in there look like, right? They're going to look like n tuples, and it'll look like maybe A1, I1, and then A2, I2, and A3, I3, and it keeps going, and then you get AN, IN. All right, it's annoying. You got to have this double subscript going on here. Okay, but that's what elements in the Cartesian product look like. Okay, so well, let's see. So let's pick some n. All right, remember this is supposed to work for all n, so we did pick one, and we want to define again some function. Let's call it h this time, from the Cartesian product a1 through an to the positive integers. Okay. And as we said, what does an element look like? So you have some A1, I1, and some A2, I2, ... and then you have some AN, I sub n. And I need to send this to some h of, well, whatever. I don't want to copy it. Well, actually, this is pretty easy based on what we've seen before. I have a whole bunch of elements, and, well, I have these indexes down at the bottom here, right? I1, I2, I through IN. What if, and those are positive integers. What if I just add those up? So I send it to I1 plus I2, ... plus I sub n. So that's fine, right? It is a function. The question is, do positive integers here have finite preimages? Well, let's say I had some positive integer, right? Maybe we'll call it some L. If L has a preimage, then L looks like a partition of itself, right? Like you've broken L up as a sum of a bunch of indices that came from, some elements we had. Well, there's only a finite number of ways to partition a natural number, right? So since L can only be partitioned, right? When we say partitioned, right, we mean written as a sum of positive integers, can only be partitioned in a finite number of ways. Furthermore, well, you could say, yeah, but if you start mixing these around, that it doesn't change the sum, right? Like if I'd have done here A sub A1 I2 and A2 I1, it's a different element of the Cartesian product, but it doesn't change where it gets mapped to. I still am adding I1 and I2 to all the rest of them, and just in a different order, but who cares? It's addition. Okay, so I could permute these around, and it won't change where I get mapped to. So that gives me more preimages. But there's still only a finite number of permutations. Okay, if I'm working in n, then there's going to be n factorial permutations. All right, so L can only be partitioned in a finite number of ways, and each partition can only be permuted in a finite number of ways. Hence, there are a finite number of H preimages. Okay, And therefore, by the countability lemma, there we go, A1 through AN is countable. There we go. All right, so I leave it to you to try to prove this fourth statement, namely that the set of all finite subsets of B is countable. All right, and we'll see you next time. Maybe we start talking about uncountability.